Hi, my name is Jasmine Chang, and today I'll be presenting about whale tails. This summer, I am a high school intern at Microsoft, working in Microsoft Research under the Cloud and Computing Storage team. In the fall, I'll be a freshman at Carnegie Mellon University, where I'll be majoring in computer science. In this video, I'll be covering the challenge, matching whales with the Siamese Network, identifying whales, and then my conclusion. For the challenge, I was using a dataset with humpback whale tails. Each humpback whale has a unique tail pattern consisting of white or dark patches, different streaks, and other patterns. And it's like a fingerprint for that whale. So the goal is to identify a whale, like the name of the whale, based on its tail. In my dataset, I had about 10,000 images of about 4,000 whales. The real-world application of this challenge is facial recognition. Like the whale's unique tail patterns, people have unique faces. Similar techniques, particularly Siamese networks, are used in both cases. My project is also an example of one-shot learning. While many neural network systems rely on hundreds of thousands of images or data points for each class, this project only had a few images per class. Likewise, if you were to create a security system based on facial recognition, you would probably only have one picture of each person you need to identify in your database. So here's an example. Are these tails from the same whale? The neural network thought that these tails were from a different whale. And that's correct. Here's another example. The neural network thought that these were from different whales. However, the correct label was that these were from the same whale. So what is a Siamese network? Well, the goal of a Siamese network is given two input images, it will tell you whether the pair is matching or not matching. It finds the differences between the images and based on that makes its determination. This is different from a classifier which gives you the label of the image. So there was a difficulty with the data that I was using. Over 2,000 whales only had one picture of each whale, and over 1,000 whales only had two pictures of each whale. Therefore, it was important to refine the data to ensure that the neural network could actually converge. Furthermore, it needed to learn the features, not just images or noise. First, the dataset had duplicate images, where multiple images were almost identical. To eliminate them, all images were converted to their perceptual hash values. Images with similar hash values were considered duplicates, and only one was kept. Next, the images were pre-processed. Based on a separate bounding box model, the images were cropped and resized. Since color was not essential for identifying patterns, the pictures were converted to black and white. Finally, a random skew was applied to help the network learn actual features. Next, image pairs were created. A positive pair consisted of pictures of whale tails from the same whale, and a negative pair consisted of pictures of whale tails from different whales. In total, there were about 9,000 training pairs and 1,000 test pairs, with exactly half of them being positive pairs and half of them being negative pairs. So here is the Siamese network model. It takes an input of an image pair labeled either matching or not matching. Each image is individually run through the neural network model, which outputs a feature map consisting of a 512-dimensional vector. Then, the difference is found between the two feature maps. A low difference means that the images are probably matching, while a high difference means that the images are probably not matching. The model's prediction is compared with the actual label. This process is repeated with thousands of image pairs. Over the course of the training cycle, the model learns and automatically adjusts its weights to better identify the features that matter. After training, the model reached about 80% peak accuracy, which meant that it correctly predicted whether or not whales were matching about 80% of the time. After 40 epochs of training, I noticed overfitting, which meant that the train accuracy was increasing while the test accuracy was dropping off. For future improvement, I'd like to try using cosine difference instead of Euclidean distance for the difference function, and changing the number of features. Currently, it is using 512 features, but perhaps using a higher or lower amount of features could help the model. So next, we're moving on into identifying whales. The goal is given an input of a test image, which is an image that the model has never seen, output the whale ID, which is the name of the whale. I tried 3 different approaches with varying levels of success. The first one was k-nearest neighbor. This found the most similar image in the training set to the test image, and then based on the label of that most similar image, labeled the test image. However, this had virtually 0% accuracy, with the correct label being in one of the top 20 predictions, or nearest neighbors. Even though the model was able to identify if the true match was the same whale as the test image, it found thousands of images were more similar than the true match. The next method was using softmax classification. A classification layer called a dense layer was added to the end of the original neural network. Using a softmax activation, it predicted the probability that the test image belonged in each class or label. This yielded about 10% accuracy. However, it did not improve with training, and this is likely due to the fact that there were too many classes. The last method was softmax with center loss. So the model would learn a center of the features for each class. This is like an average. There was an improvement from about 10% to about 20% accuracy. In the future, I'd like to investigate if center loss could be used with the Siamese network. In conclusion, here are my main takeaways from doing this project. First, when working with difficult data, it is important to filter the data and pre-process it in order to ensure that the network can learn. Second, it's to be open to research and learning. Reading research papers is not as scary as it seems. And lastly, it's to experiment with different ideas and different techniques, and through the process to be patient with yourself. Thank you for listening to my presentation. Thank you to my mentors Jin Lee and Hongji Lee and the Microsoft High School Intern program.